Okay, so good morning, everyone. So I'm Mathy Vanhoef. First and for all, thank you for the introduction. Thank you for allowing me to speak here. So today I'm going to talk about my research on attacking WPA2. And in this presentation, I'm also going to present a few more implementation-specific improvements of the attack that we discovered. But so first and for all, how is this talk structured? First, I'm going to explain the general idea behind the vulnerability that we discovered. And specifically, I'm going to explain how the attack works when applied against the four-way handshake. Then I'm going to discuss in a bit more detail what the actual practical impact is in practice of our findings. Then I'm going to discuss about a few new improvements that we discovered. And finally, I'm going to end the presentation with a few lessons that we can learn from this research. So let's get started with explaining the attack against the four-way handshake. And this will explain the general idea behind the attack. And once you know the general idea, you can also understand how it works against other handshakes that are used in a Wi-Fi network. So the question you probably all have at this point is, okay, what is this four-way handshake you are talking about? And the four-way handshake is used in a protected Wi-Fi network to provide mutual authentication and to negotiate a fresh session key. So here, mutual authentication means you both verify the identity of the access point, meaning you are connected really to the network that you want, and the access point also verifies that you have the proper credentials and are allowed to connect. And at the same time, we negotiate a fresh session key, and this session key will be used to encrypt data frames once the four-way handshake has completed. So if you would have asked me a year ago that whether this would seem secure and whether WPA2 would seem secure, I would have said, yeah, it seems secure, because WPA2 existed for more than a decade. And if we ignore dictionary attacks against a weak password, there are no known security issues. In other words, if you have a Wi-Fi network and you pick a strong password, or if you use enterprise authentication with a username and a password as login, then you're fairly good. On top of that, there are even formal proofs of the four-way handshake anti-encryption protocol that is executed after it, which state that these algorithms, this design should be secure. So in a sense, it's really surprising that we discovered this, because there is all this evidence pointing towards that it's secure. But of course, we did find a vulnerability, and in order to explain how this vulnerability works, I'm going to discuss in a high level how the four-way handshake works, and then we can explain what a key reinstallation attack really is. So let's say that we have a client here on the left, and it wants to connect to the access point on the right. Now, if you're just using an ordinary home network where authentication just happens using a password, then we can immediately execute the four-way handshake. But in case you have an enterprise network where you log in using certificates or using a username and password, then the first thing that happens is that an 802.1x authentication handshake is being executed. And luckily, we don't need to know the details about this. In practice, this would mean that there is first, for example, some kind of radius handshake. And the end result is there is some shared secret between the client and the access point. And once both these devices have this shared secret, then we can execute the four-way handshake. And as the name of the four-way handshake implies, it consists of 4 messages. And the first 2, the purpose of them is quite simple. They simply exchange a random number between both devices. And this random number is called the nonce. So first here you have the access points. It sends the A nonce towards the client. A nonce stands for access point nonce. Then the client in return generates a random number itself as well. It's called the supplicant nonce, the S nonce, where supplicant is just a synonym for the client. And then it transfers that random number to the access point. And once both these devices have these random numbers, then they can combine that random number with the shared secret behind shared between these 2 devices to generate the PTK. And the PTK, that is the fresh session key, which will later on be used to encrypt frames. Okay, so before we continue, there's one thing I want to clarify. That's you might have also heard about this research as key reinstallation attacks, forcing nonce reuse, and WPA2. I want to clarify this nonce reuse does not refer to the A nonce on S nonce that I'm talking about here. So for now, we're going to assume that the A nonce on S nonce are securely generated, they are random, they cannot be predicted, and so on. The nonce reuse that the title refers to will refer to nonce reuse while encrypting data frames, and I will come back to that later. Okay, so that's the first part of the four-way handshake. The second part is essentially just to confirm that both parties generated the same session key. And on top of that, here in message 3 of the four-way handshake, you can also see that the GTK is transported from the access point to the client, and the GTK, that's the group key. That's the key that will be used to encrypt broadcast and multicast frames. So that key is also transported to the client during the four-way handshake, and specifically in message 3. And at this point, both parties know the session keys, so they can install the keys and they can start exchanging encrypted data frames. So now the final piece of the puzzle that we need to know in order to understand these key reinstallation attacks is how are frames encrypted in a Wi-Fi network? And to explain this, let's take that we want to send this plaintext data and we want to encrypt it and send it. And independent of the specific configuration of your protected Wi-Fi network, this encryption will, at a very high level, all use the same structure, basically. So the first step that happens is that we take this secret session key that was just negotiated and we combine it with an incremental packet number. And this packet number is also called a nonce. And the idea is that by combining these two, we can generate a unique key to encrypt every individual packet. So how do we then use this unique per packet key? Well, it's quite straightforward. We simply use a stream cipher to encrypt it. So in practice, that means we take this per packet key, we use it to derive some key stream, we XOR that key stream with the plaintext data, and we get the encrypted data. And of course, when we send this encrypted data, we also include a plaintext header so we know which nonce, which packet number was used. And at a high level, this construction is fairly simple, but it makes one essential assumption, and that's that under a specific session key, under a specific TPK, a packet number should never be reused. Now, why is that the case? Why should a packet number never be reused? And you can sort of read the answer here from these slides, because if a packet number is ever reused, it means we generate the same per packet key, which in turn means we generate the same key stream, so we have key stream reuse. And when in a network protocol you have key stream reuse, in practice that means you can start decrypting frames where if one message you know the content, you can derive the key stream there and use that derived key stream to decrypt the frame. And we'll come back to that later. For now, just remember, if there is key stream reuse, that's bad. And in this case, that means that if there is packet, if the nonce, the packet number is ever reused, we're also in trouble. So now the big question is, can this packet number ever be reused? And as I mentioned, the packet number is incremented by 1 for every packet you send. So far that seems okay. So the only question that remains is to what number is this packet number initialized? And again, the answer is quite straightforward here. When you install the key, the packet number is set to 0. And that makes a lot of sense. I mean, you start the counter at 0, you always increment it by 1, so surely this number is never reused, right? But we did find a way to make the client reuse that packet number. So let's explain the attack now against the four-way handshake. So we again have the scenario where we have the client on the left here, it wants to connect to the access point on the right. But in this case, we also assume that there's an evil attacker nearby that's going to attack the four-way handshake. And the first thing that the attacker will do is it will establish a so-called channel-based man-in-the-middle position. And this man-in-the-middle position is not yet used to decrypt frames. It will only be used to reliably manipulate Wi-Fi packets, so we can reliably block some packets from arriving. So how does that man-in-the-middle position work? Well, let's say the access point, so the real network, is operating on channel 6. Then what the attacker does, it clones this network on a different channel. So in practice, that means that every frame that the access point transmits on channel 6, we will retransmit that on channel 1. Now the idea is that we can really force the client, we can force the victim into connecting to our network on channel 1. And then the attacker can forward also the frames that the client is sending to channel 6 to the real access point. And that would mean that all frames that the client on access point is sending will pass through the adversary, and then the adversary can decide whether to forward packets or to block packets or to delay packets. So again, to be clear, the adversary is not yet decrypting anything. Okay, so let's assume we have this man in the middle position, and the client wants to connect to the access point. In case we are attacking an enterprise network, we first have this 802.1x authentication stage, and here we don't do anything special. We just forward the frames and let the client and access point execute this handshake. The same is true for the first 3 messages of the 4-way handshake. We simply forward them between both devices. So up to this point, nothing really special is going on apart from this man in the middle position. But when sending message 4, it becomes interesting. The client will send message 4. However, we, as an attacker, will not forward this message to the access point. And now we are in an interesting position, because from the perspective of the client, the 4-way handshake has completed. It received all the messages of the handshake and it replied using all of them as well, meaning it thinks the 4-way handshake is done and it will install the session key and the group key as well. However, we block the message from arriving at the access point, so the access point thinks that the handshake hasn't completed yet. In particular, it will think either message 3 or message 4 got lost somehow, and it will try to recover from that situation. So let's make some space here. The way it recovers from that situation is it will retransmit a new message 3 towards the client. And the Wi-Fi specification is very clear what should happen now. Namely, if the client receives a retransmitted message 3, it should accept it and it should reply using a new message 4. And on top of that, after it, it should reinstall the session key as well. Now, as you can see here, message 4 here is encrypted. Now, why is that the case? Well, these handshake messages, they are ordinary data frames, and we already installed the session key to encrypt data frames. So this handshake message is already encrypted. Now, if these implementations would be following the Wi-Fi standard, this message 4 should not yet be encrypted. But anyway, we're going to later on rely on this assumption that message 4 is encrypted, and in practice, all devices will send message 4 in an encrypted fashion. So what we have now is we have message 4. It's encrypted using a packet number of 1. And now we are reinstalling the session key. And when reinstalling this encryption key, the packet counter, the nonce, is reset to 0. And this is where it goes wrong. Because if the client now sends a new packet, well, this packet number got reset to 0, meaning if we now send a packet, we just increment it by 1, and then encrypt the frame using a value of 1. So if the client now sends another data frame, we are reusing the nonce value of 1. So the same nonce is used, that means the same key stream is used, and that means that we're in trouble. So I'm now going to explain a technique which we can use in this case to decrypt this data frame that is sent here. So in order to decrypt this data frame, we need to recover the key stream corresponding to this nonce value of 1. Now, if you very carefully look at this diagram, you can find a way to recover the key stream corresponding to the nonce value of 1. So maybe some of you are already seeing it, but what we have here is that we have first message 4 in plain text, then we have a retransmission of message 4, which is encrypted. Now there is a small difference between these two packets, but most of the fields are the same. So we have the plain text, we have the ciphertext, we just XOR them, and we have the key stream corresponding to the nonce value of 1. Then we just take that key stream and we can decrypt this data frame. And there you go, we decrypted the packet, so we have now broken WPA2. So if the client is sending sensitive information in this data frame, for example, if it's a plain text HTTP request, we can start recovering cookies or maybe passwords and so on. Of course, if the client is using SSL, you have another layer of protection, then you wouldn't recover sensitive information. But there are still quite some unprotected websites or quite some email traffic which is not yet encrypted where we would be able to recover data. So let's discuss that practical impact a bit more, because now I only discussed that you can decrypt data, but you can do other things as well. So let's assume that you have a device that is vulnerable to a key reinstallation attack. So as I mentioned, this can be a client device, for example, a smartphone, a laptop, or these days even a Wi-Fi. You have Wi-Fi toasters. They support Wi-Fi as well. But an access point can also be vulnerable against key reinstallation attacks depending on the handshake you are exploiting. So let's say you have a device that is vulnerable. Then there are two things that can happen in general. The first thing is that what we discussed just now, if this device ever transmits encrypted data, then we can force this device into reusing a nonce by triggering a key reinstallation. And when we have this nonce reuse, we can decrypt frames like I explained. However, there's also a second thing that goes wrong, and that's when you reinstall a key, the so-called receive replay counter is also reset to 0. And as the name implies, this receive replay counter is used to detect if an adversary is replaying frames. So if it's just taking a previously frame and retransmitting it without modifying anything. And normally this replay counter detects these replays, but of course if we can reset this number back to 0, we can start replaying frames towards the device under attack. So those are the two general things that can happen in a key reinstallation attack. We can decrypt frames and we can replay frames. But in practice, the specific impact also depends on a few other factors, and I'm briefly going to discuss those as well. And the first important factor is which encryption algorithm we are using. And the most widely used algorithm here is AES CCMP. In practice, nearly every Wi-Fi network is using that, and in this case, the impact is, in a sense, limited to just decrypting and replaying frames. Now, of course, that's already bad enough, but at least luckily, an adversary is not able to forge frames and eject forged frames into the network. Because if we would have still been using the older WPA2 algorithm, in that case, if there's nonce reuse, we could recover the message integrity check key, which is just an authentication key, meaning we would be able to forge messages that appear to be sent by the device under attack. So we got lucky here that now we're using AES CCMP, because otherwise the impact would have been worse. Another factor that influences the impact of the attack is which specific handshake we are attacking. Because, for example, the group key handshake, which is the handshake used to transport a new group key to the client, that may also be vulnerable to a key reinstallation attack. And if we are attacking this handshake, we would be attacking the client, meaning we would trigger a key reinstallation in the client. However, the impact is limited in this case because the client never sends real broadcast frames. So that means in practice, we cannot force nonce reuse when encrypting broadcast data frames. Now, this may be a bit tricky to understand, but the conclusion here is that if you are attacking the group key handshake using a key reinstallation attack, the impact is limited to replaying broadcast frames. We cannot decrypt broadcast frames. We can only replay them towards the client. And the impact against the four-way handshake, well, I already discussed that. In that case, we again attack the client. We can decrypt and replay frames. And depending on the cipher suite that is being used, we can also forge frames. So for example, if WPA2 is still being used, which you should not use anymore, then we would also be able to forge packets. Then the final element that influences the specific impact in practice is which specific operating system you are attacking. For example, if you are targeting an iOS or Windows device, then their implementation of the four-way handshake deviates from the standard. And because of that, the four-way handshake of them is not vulnerable. And specifically, what they do differently is that these two operating systems, don't accept a retransmission of message 3 of the four-way handshake, meaning we cannot use this retransmitted message 3 to trigger a key reinstallation. So in a sense, that's funny here because they don't follow the specification, and because of that, they are more secure. It's a bit of the exception. But there are two important remarks that I do want to give here, and that's first and for all, they do have a vulnerable implementation of the group key handshake. And with iOS, well, iOS 11 does properly implement the four-way handshake. Now they do follow the standard, which unfortunately means iOS 11 is insecure. We cannot attack that. Now, there's also a very interesting situation going on with Linux and Android. If you look at the Wi-Fi client that is used by Linux and Android devices, it's called WPA supplicant. And WPA supplicant is doing something even more funny, because instead of reinstalling this secret key that's being negotiated, when this Wi-Fi client receives a retransmitted message 3, it will just install an all-zero encryption key. Meaning the victim is using a predictable key, it's using all zeros. We as an attacker know the key, so any data that an Android or Linux device would now send, we can just decrypt it. And of course, we can also send any data we want towards the client as well. So you might be surprised why this is happening. Unfortunately, I'm not going to go into detail here, but there's actually a reasonable explanation why this goes wrong. If you know the details, as a programmer, you would be like, yeah, I could have made that mistake as well. So it looks funny at first sight, but it's understandable. Okay, so we now covered the general idea behind our attacks. So let's discuss a few improvements that I discovered over the past few months. Now, these improvements, they're not attacks against the standard, they're attacks against specific implementations, but these new attacks sometimes make it easier for an attacker to exploit these vulnerabilities. And the first idea that we had here is that, okay, when we previously were attacking the four-way handshake, we were retransmitting message 3, and we were trying to use that to trigger a key reinstallation. Why not also try to retransmit message 4 and try to use that to trigger a key reinstallation? But now we can use that against the access point. So again, if we have the diagram here, previously we were retransmitting message 3 to trigger a key reinstallation in the client. Why not also try to retransmit message 4? And the Wi-Fi specification itself says that if the access point receives a retransmitted message 4, it should just ignore that. But of course, we all know that implementations can be buggy, so who knows, there is an access point that does accept a retransmission of message 4 and will, in response, reinstall the key. And we indeed found one router, one access point that is doing that. And more specifically, we found that certain MediaTek drivers that implement the four-way handshake, they accept a retransmission of message 4. And on top of that, we don't need to use some kind of special tricks. For example, we don't need a man-in-the-middle attack to exploit this. We can just take the message 4 that was sent initially, then take it without any modification whatsoever, and just replay that. So if you want to attack these access points, we don't need a middle position. It's very easy to do that. And the impact here, even though we are targeting one specific driver, this driver, if you look it up online, is used by a lot of devices. So there are quite some vulnerable products. For example, you have your ordinary home router that may be vulnerable, but you also have a bit more special devices. For example, this smart power plug is also using these MediaTek drivers. Now, I wasn't able to specifically test this device, but unless they modified their drivers and made custom modifications, this device would be vulnerable as well. So you can imagine if you have a device here which has a smart power plug where you can send commands to it to activate or deactivate the electricity. If that's vulnerable, that would of course be a bad thing. Now, another idea, and well, this is mainly an observation we had, is that during the handshake, we also have these two random numbers that are being exchanged. And initially, we assumed that these random numbers were generated properly. that they were predictable, that were not predictable, and that they're always different. But of course, in practice, implementation might reuse the same S-nonce or A-nonce here. And this would be problematic because if an A-nonce or S-nonce is ever reused, then we might be able to force the client or the access point to again negotiate exactly the same session key as before, meaning we would again have a key reuse where a key would be reinstalled. So specifically the situation we have is that when a client is already connected to a network, the access point can decide to execute a new four-way handshake to refresh the session key. And during this rekey, during this new handshake, both implementations should be using a new A-nonce and S-nonce. And during this new handshake, exactly the same messages are exchanged, except both parties should be using a new A-nonce. However, if we look in practice, and we noticed this while we were testing the patches of macOS, we noticed that macOS properly patched against our attack, properly patched against the KRACK attack. However, during a rekey, macOS was reusing the previous S-nonce value. And that's a bad thing. Before I'm going to explain how this can be abused, I want to notice that the recent version of macOS patched against this. So, of course, remember to update your devices. But how can we exploit that? Okay, macOS uses the same S-nonce. Is that a problem in practice? Well, if the access point uses a fresh A-nonce, then we are still negotiating a new session key. So if the access point is using a new A-nonce, then it's not immediately a problem. However, we noticed that Linux host APD, which is the open source access point implementation used on Linux and also on a lot of proprietary devices as well, we found that this implementation is reusing the A-nonce value. This means that if an old macOS version is connected to an access point using host APD, and if that network was configured to refresh the session key, for example, every 10 minutes or every hour, that means every 10 minutes or every hour, they would negotiate exactly the same session key. Because the same A-nonce is used, the same S-nonce is used, the shared secret between both devices is the same, so we would generate exactly the same key. We would reinstall the same key, meaning we would also get key stream reuse, and we're in exactly the same problem. So this is a bit of an interesting situation, because even if an attacker wasn't present, a device was reusing a key stream. So if you have a macOS and you were connected to one of those networks which refreshed the key, say, every hour, then if someone would have captured your traffic, they could now go back in time and decrypt large parts of it. So you now may be wondering, okay, what if I'm still using an old macOS version? Can that also be attacked? Let's say you want to attack someone, they're using an old macOS version, but they're now connected to an access point which properly generates a new A-nonce. Well, it's possible as an adversary to replay an old handshake towards a macOS device under specific cases, but it's a bit tricky to do. So the summary here is, even if the access point is implemented properly, you can abuse this S-nonce reuse against macOS, but it's difficult to do in practice though. So after noticing that macOS here didn't fully patch and prevent these key reinstallation attacks, we also had the idea of properly auditing other patches of vendors. And the first thing that we noticed here is that we had quite a few reports where people were saying that, hey, we applied your patches to WPA supplicant, the Wi-Fi client used in Linux and Android, but your script says that our client is still vulnerable to group key installations. How is that possible? We were worried about that as well, because there are two explanations why our script might say an implementation is still vulnerable. The first is our patches are flawed, which would be a big problem. The second case why our test might say that an implementation is still vulnerable is because these devices may accept replayed broadcast frames. That's because our scripts indirectly test whether a group key is reinstalled, because our scripts just test whether the device will accept replayed broadcast frames. So we were thinking that, okay, it might be possible that the device just always accepts replayed frames. Now, initially we thought this would be very surprising because detecting replayed frames is trivial. You just take the packet number that is in your received frame, you just do an if test with your counter that you store locally. If the number you receive is smaller than the number you previously received, you just ignore the message. So this is just an simple if test. So surely no one forgot this, right? But then we tested devices in public. For example, we tested this micro USB adapter, and it indeed accepts replayed broadcast frames. So now you might be thinking, okay, this is just one device. It's maybe even a cheaper device. So of course, cheap devices might be buggy. Then we tested another device. This is a more popular device. It's commonly used by hackers as well because it has a wide range. You can receive networks from far away. And again, this device accepts replayed broadcast frames. So now you might be thinking, okay, maybe if you use an external USB Wi-Fi device, then you're vulnerable. But if you just use your original Wi-Fi chip, then that's properly tested. But then we tested a Nexus 5X phone, and here the original firmware also accepts replayed broadcast frames. And we tested 16 devices in total, and half of them indeed are vulnerable. They just accept replayed broadcast frames, which is very surprising to us. And we think the reason why this goes wrong is because they implement encryption in hardware or in firmware, and there's a bug somewhere in that hardware or firmware. Because if, for example, with these USB devices, if we then force software encryption, then they are no longer vulnerable. So if you want to defend against this, you can try to enable purely software encryption and disable hardware encryption. Now, we also discovered a related issue here, which would again allow us to replay broadcast frames. And that's that some devices do not properly install the group key. Now, what do I mean with this? Well, let's go back to the four-way handshake. We have here that the group key is transported in message 3 of the four-way handshake. And not only is the group key transported, but also the current replay counter associated to this group key is included. Because the access point may already have used this group key to, for example, encrypt 100 frames, meaning the current value of the replay counter is 100, and the client also needs to know that value. So what should happen is that the client installs the group key, and it also installs a replay counter value of, in my example, 100. But we found that some devices just install an all-zero replay counter. And specifically, I tested this against my old smartphone, a Samsung S3. And this indeed always just installs an all-zero replay counter. And very recently, I also discovered that a quite popular client has this vulnerability as well. Unfortunately, I only recently discovered this, so I only recently was able to inform them. So I'm not going to disclose the specific vendor yet. I'm going to give them some time to patch it. But this confirms that even a popular, fully updated device can have this vulnerability. So now the question is, okay, how can you abuse this? And the idea here is quite straightforward. Let's again say we have a client, it's connecting to an access point, it executes the four-way handshake as always, and if it's vulnerable, it will install the group key, and it will install it using an all-zero key. So far, nothing special really happened, but let's say the access point then sends some broadcast data. And we, as an attacker, want to replay that broadcast frame towards the client. So I guess some of you already know how to perform the attack now. So maybe some of you have an idea how to do this, but it's quite simple. What you do as an attacker, so you don't need a man in the middle position here. You just need to be near the victim. And what you can do as an attacker is you just send a deauthentication frame to the client. So you're forcibly disconnecting the client from the Wi-Fi network. And then every operating system will immediately try to reconnect so the client doesn't lose internet connection. So the client will execute a new four-way handshake with the access point, and when executing that new four-way handshake, it's effectively resetting the replay counter of the group key to 0. And at this point, as an attacker, we can just take that broadcast data frame and just replay it. And there you go, that's how you attack it. So it's quite straightforward, you don't need a man in the middle position, and you're done. So now one important thing I want to discuss as last part of the improvements of our attack is, yeah, okay, so we have quite a few attacks here where we can replay broadcast and multicast data, but you're probably wondering, like, is that really useful in practice? And maybe in a properly secured network, replaying broadcast frames, the impact of that is something you can ignore. Let's be honest there. However, there are certain cases where this ability is very problematic. And to give you one example of that, I'm going to discuss this smart power plug, the smart power socket. And here you can control it using an Android app over Wi-Fi. And it's implemented in a very interesting way. Instead of just sending commands directly to only this power plug, it's using broadcast UDP to send commands to this device. Now, as a programmer, this is very weird because you want to send commands to one specific device, but it's using broadcast UDP and it's sending the destination MAC in the payload of the UDP. So this might seem very weird. And the reason they might be doing this is because previously they used this protocol to command a lot of devices at the same time. For example, you can imagine that you have 4 light bulbs, you want to turn them off and on at the same time. In that case, it would make sense to use broadcast. So maybe they took that protocol that they already had and then just modified a bit to work to just instruct one device. But anyway, we now have a protocol where broadcast frames are used to send commands. And in this case, they use a challenge and response protocol to add some security to it. But we can exploit this attack using our using the other attacks that we previously discussed to replay broadcast frames. So let's discuss how we would attack this device. So let's say we have our Android app here, and it wants to, for example, turn on or off the electricity to our smart power socket. Then, well, we have the ordinary handshake that is being executed. So how the protocol works, it will first send a command request saying, hey, I want to execute a new command. The power socket will generate a challenge number. It will generate an ID, an ID. It will transport this ID back to the Android device. The Android device will then reply using a confirm request, and it will include this ID as a form of basic authentication in a sense. And if the power socket notices that this ID, this challenge number in the confirm request packet is the same as the ID it previously generated, then it will run the command and it will send the result of the command back to the Android app. So how can we exploit this? Well, let's make some space. It's very simple. We just take the confirm request command. It's a broadcast UDP packet. We can replay that using our attacks. And the power socket will receive that packet. It will check the ID. But of course, it didn't refresh the ID. So this ID is still valid, meaning it will accept this confirm request packet. It will again run the command, which means that, if we have a command to turn on or off the electricity, we can execute that command. Now, initially, I was planning to make a quick video of how this attack worked, but yeah, it would be cool to show this, but I decided instead to improve my scripts that you can use to test whether a device is vulnerable. So if you're wondering whether your device is vulnerable to one of these new implementation-specific improvements, you can visit my repository here, and that contains the script where you can test whether a device is vulnerable to replaying broadcast frames, whether it's vulnerable to a key reinstallation attack, and so on. Now, there is one annoying thing here when you are using these scripts, and that's These scripts are used to detect bugs in certain Wi-Fi devices. But when you use this script, you have to be sure that as a tester, you don't use a buggy Wi-Fi dongle yourself, because otherwise that might interfere with the tests. So basically, if you use these scripts, disable hardware encryption, because otherwise our tests might give the wrong results, which is annoying. Or just use a proper Wi-Fi dongle. The page mentions some Wi-Fi devices that we use that we know that are working properly. And as an additional note, if you look at my GitHub page, there's also a repository that implements an attack against Android on Linux. So I previously mentioned during my presentation that Android on Linux, they install an all-zero encryption key. And at that point, you can intercept whatever data they are sending. And when I initially disclosed this research, I didn't make those scripts public yet, because the impact is quite high. But yeah, if you look at my GitHub profile, you will find this exploit somewhere. So if you want to attack Android on Linux devices that are still not patched, you can take that code and execute it. So it's not very reliable. It works in a lab setup, but if you improve it, you can really attack devices. So as the last part of the presentation, let's discuss some lessons that we can learn from this research. And the first lesson here, and this is really the most interesting part I find about this research, is that the four-way handshake was formally mathematically proven as secure. And the same is true for the encryption protocol AES-CCMP that is executed after this. So we have this formal proof, but we still managed to break it. So what went wrong here? Well, what went wrong here is that these two components were proven to be correct separately. But when we combine them, that's where it goes wrong. Because if we look at the proof of the four-way handshake, it proves that the generated key remains secure. And that's indeed the case. As an attacker, we cannot recover the password of the network. We cannot recover the session key. We're only reinstalling this key. The same is true for the encryption protocol. There, the proof states that if we install a key only once, then the encryption protocol is secure. However, we precisely exploit this interaction between these two components. We abuse the four-way handshake to make the encryption protocol install the key multiple times, and that's where it goes wrong. Now, another lesson that we can learn here is, well, the keynote of today already mentioned this. We had to coordinate this vulnerability with a lot of affected parties, and that's not easy to do because there are several difficult questions to answer. For example, how many people do you contact? How much time do you give? These are all difficult questions. And if you want some guidelines on this, I recommend reading this document. They give at least some strategies which you can rely on. Now, my personal remarks here would be that if you do this, the end goal is to protect the users. It should not be to protect the reputation of the company. And of course, there are various opinions here, so this is something to have discussion about still. So to conclude the talk, the key reinstallation attack really is a flaw in the WPA2 specification itself. The improvements we discussed today are implementation specific. What I find most interesting that, yeah, it was proven correct, but yeah, we managed to break it anyway. So I still think that formal verification is very useful. We should still be doing that, but it's not because something is proven secure that it's indeed secure. We should also audit the proofs on the implementations. And it's not just a theoretical crypto attack. We can attack devices in practice. It's just not some pure theory stuff. And finally, I recommend everyone to update your devices to protect against it. So if there are any questions, feel free to ask.